This is Donna Nelson at the University of Oklahoma, and we are on the second lecture from my organic chemistry class, which comes from chapter 20, carboxylic acids and their derivatives. So let's look at what this second lecture is going to encompass. So an introduction to the carboxylic acid derivatives, that's going to include their nomenclature and reactivity of carboxylic acid derivatives. And that looks like only 2 sections, but it's not really short because there are many important carboxylic acid derivatives that we're going to have to cover. So let's look at these. First, remember the reduction of a carboxylic acid to an alcohol. You're actually going from, here you have 3 bonds to oxygen, now you just have 1 bond to oxygen. And so there is a change in the oxidation state of carbon. However, in converting a carboxylic acid to a carboxylic acid derivatives, notice that there is no change in the oxidation state. We are going from carbon bonded to 3 highly electronegative atoms to carbon being bonded to 3 highly electronegative atoms. And so there's no change in the oxidation state. So this is going to be a little bit different than that which you saw in the reduction to give you alcohols. So let's look at these reactions and the different carboxylic acid derivatives which there are and their nomenclature. So the most common carboxylic acid derivatives are the acid halide, acid anhydride, ester and amide, and then also the nitrile is frequently incurred. But these are the 4 that are most commonly discussed and considered. These can all be interconverted and are just extremely important in organic reactions. So let's look at those. Acid halides and anhydrides are very reactive. Here they're listed in their order of reactivities. Acid halide is most reactive, the amide is least reactive. And so these 2 are most reactive. The anhydride is almost as reactive as the acid halide, but not quite. And so these 2 are much less reactive. And so that means that they're more easily controlled in the lab, and they will be more selective. These acid halides can react violently even. So esters and amides are abundant in nature. Acid halides and anhydrides are not common among naturally occurring compounds in contrast. And so the esters frequently are very fragrant, and they are have appealing odors. So, for example, methyl butanoate smells like pineapple, isopenyl acetate, banana, butyl acetate, pear. This is certainly the common name here, isopentyl. So not the IUPAC name by all means. So proteins are comprised of repeating amide linkages. You can see them here. The structure of proteins. Many other compounds feature amides, including natural sedatives like melatonin. Here you can see it. To name an acid halide, you replace the ic acid with L-bromide. Acetic acid goes to acetyl bromide, or benzoic acid goes to benzoyl chloride here. If an acid halide group is connected to the ring, the suffix carboxylic acid is replaced with carbonyl halide. So cyclohexane carboxylic acid, cyclohexane carbonyl chloride. That's a nice example. Acid anhydrides are named by replacing acid with anhydride. So this is an anhydride that is made by combining or reacting two molecules of acetic acid. Here is an anhydride that is made by simply cyclizing succinic acid. So succinic acid goes to succinate anhydride. You can also have mixed anhydrides where the two ends are not the same. So here, this is an asymmetrical anhydride, and it's named by listing the acids that would contribute to this molecule in alphabetical order, followed by the word anhydride. So acetic, benzoic, anhydride. So you can see the anhydride linkage here in the middle. Esters are named by using the alkyl group attached to the oxygen, followed by the carboxylic acid's name with the suffix -ate. So here, if you replace the proton with an ethyl group, so now this is called ethyl, and since it's a derivative of acetic acid, it is named acetate. So this will always be acetate, regardless of the group that is attached to oxygen. Malonic acid, so this is a symmetrical diester that is being formed, and so both of the protons that are attached to oxygen are being replaced by ethyl, so this is named diethyl malonate. The malonic acid is switched to malonate. The same rules apply if the ester is connected to a ring. So here you can see the carboxylic acid is connected to a cyclohexane. This is called cyclohexane carboxylic acid. And so now if you have the ester connected to the cyclohexane ring, this part becomes cyclohexane carboxylate, and there is a methyl group attached to the oxygen. So here is the methyl that corresponds to that methyl group. So this is methyl cyclohexane carboxylate. Amides are named by replacing the suffix ic acid with amide. So when the hydroxyl group is replaced by the amino group, this acetic acid becomes acetamide. The same thing with benzoic acid being functionalized with an amino group. Now this benzoic acid becomes benzamide. Benzamide. If the amide group is connected to a ring, the carboxylic acid is replaced with carboxamide. So cyclohexane carboxamide. Here is the amide functionality that is directly attached to the ring. More on naming amides. If the nitrogen of the amide group bears alkyl groups, like here the nitrogen is bearing one methyl group. Over here, the same molecule, except the nitrogen is bearing two methyl groups. So Without the methyl, it would be acetamide. With this methyl, it will be N-methyl acetamide. The N means that the methyl is attached to nitrogen. This is N,N-dimethyl. Both of the methyls are attached to nitrogen. N,N-dimethyl acetamide. So here, the methyl group doesn't have a number as a locant. The N, which stands for nitrogen, is the locant. Nitriles are named by replacing the suffix ic acid, as in acetic acid, or oic acid, like benzoic acid, with onitrile, acetonitrile. So here is the nitrile, here's the nitrile. This is benzonitrile, acetonitrile, benzonitrile. Now, as I mentioned earlier, the acid halide is most reactive of these carboxylic acid derivatives, then the anhydride, then the ester, then the amide. And these are very electrophilic at the carbonyl carbon. The reactivity is determined by induction and resonance and sterics and the quality of the leaving group. So let's look at some of the reactions that these will undergo. So acid chlorides are the most reactive. By induction, the chlorine is going to withdraw electron density from the carbon, which is already partially positively charged, because it is bonded by two bonds to oxygen. So this carbon, which even in a carbonyl, a ketone or an aldehyde, is partially positively charged and pretty reactive. Now it's bonded to a chlorine. The chlorine is going to withdraw electron density, making the acid chloride even more reactive. So here is the typical resonance structure that you would draw if you had, just say, a ketone or an aldehyde. But now you have chlorine attached, and so you have a pair of pi electrons. The chlorine can donate a pair of electrons to the positively charged carbon, but it's not that much of a donor in this molecule, and so this is not a significant resonance contributor. And so it does not satisfy the positive charge sufficiently to render the carbon less electrophilic. Amides are the least reactive of the derivatives. Here you can see that the typical resonance structures for the carbonyl can be drawn, and you put a positive charge at the carbon, negative charge on oxygen. However, now nitrogen does donate electron density significantly to satisfy that positive charge, and so you have a positive charge generated on nitrogen, and this is a significant contributor, and so that does make this carbon less electrophilic, and so less reactive therefore. And so amides are not very reactive because they're not bearing, the carbon is not bearing such a large positive charge. So remember, in your carboxylic acid derivatives, you've got a group here that can function as a leaving group. You can go back and look at those. We're going to see these function as a leaving group. All of the groups attached to the carbonyl carbon can function as a leaving group. That is entirely different from the situation with aldehydes or ketones. Here you cannot have, one does not see hydrogen function as a leaving group if the carbonyl is attached. and the alkyl group does not function as a leaving group. You are going to see, however, that carboxylic derivatives, when a nucleophile attacks, you will see the group attached to the carbonyl depart as a leaving group. It will never happen in the case of aldehydes and ketones, but it does happen in all of the carboxylic acid derivatives. So that's why this is an entirely different class of molecules. An entirely different reaction is available to it that was not available to aldehydes and ketones. So here we see what is happening. This is called nucleophilic acyl substitution. There are two steps here. Notice that the first step is the nucleophile comes in and populates the antibonding orbital. The pair of electrons in the pi bond moves out onto oxygen, and you have formed this new bond to the nucleophile. Now you have the leaving group. Here we have a group that can function as a good leaving group, and so you have loss of the leaving group. The carbonyl is reformed, and so the nucleophile has been substituted for the leaving group. You see this tetrahedral intermediate. This is a true intermediate. In some cases, it may need to be that the leaving group will have to be protonated in order to lose the leaving group, but that's not a problem. We see protonation and deprotonation all the time. Those are very common steps in organic chemistry. So, in the aldehydes and ketones, you'll see H- and, or an anion, a carbon anion, can't be expelled as leaving groups. So that's why this is possible with the carboxylic acid derivatives, but this is not possible with aldehydes and ketones. So now, let's look at a specific example. We have the incoming methoxy anion. So this is methoxide coming in. A pair of electrons occupies the antibonding orbital, attacks that carbon. The pair of electrons in the pi bond moves out onto oxygen, forming a negative charge at oxygen. And you can see that a carbon-oxygen bond has been made to the methoxide, and you can see it right here. Now, the chloride is still attached. This is the tetrahedral anion. So this is the tetrahedral anion, which is now going to reform the pi bond. Right here, you can see it reform. And since carbon can only bear 4 bonds, chloride must depart. And it does. So this is where you've definitely had a substitution. Methoxy has been substituted for chloro, but not in one step. This is not a concerted reaction. It is stepwise. So let's look at this. Again, as I just said, this is not a concerted process. Remember that we're going to start looking at some mechanisms. Remember, as we're doing this, under acidic conditions, negative charges will not be formed. Under basic conditions, positive charges won't be formed. Sometimes a proton transfer may be necessary, and you'll just have to be flexible and be able to look at it and recognize if a proton transfer is needed. And so that takes care of the introduction to carboxylic acid derivatives, and now we'll go on in the next lecture to look at some of the specifics. So this concludes lecture 2, and we will start in lecture 3 next.